Imagine a beam of light racing across the universe. Now imagine chasing after it faster and faster until you catch up. It sounds like a child's fantasy, but this mind-bending possibility is at the heart of Albert Einstein's theories of relativity, ideas that shattered our understanding of space and time. Einstein, with his iconic unruly hair and a thought process as limitless as the cosmos, dared to question the very fabric of reality. Before Einstein, time was considered a constant, ticking away at the same rate for everyone, everywhere. Space was a static stage where the events of the universe unfolded. But Einstein, in a stroke of genius, realized that space and time were not separate entities but rather intertwined threads in the grand tapestry of the cosmos. His theories of special and general relativity, unveiled in the early 20th century, were not mere refinements of Newtonian physics, but a revolutionary paradigm shift, a quantum leap in our understanding of the universe. Einstein's theories, often perceived as arcane and complex, are rooted in elegant simplicity. They urge us to shed our earthly prejudices about space and time and embrace a more expansive, more mind-boggling perspective, one where time can be stretched, compressed, and perhaps even traversed. Like a cosmic magician, Einstein taught us that the universe is far stranger, far more wondrous than we could have ever imagined. Einstein's special theory of relativity, published in 1905, begins with a deceptively simple postulate: the speed of light in a vacuum is constant for all observers, regardless of their own motion. This might not sound revolutionary, but its implications are profound. Imagine two people observing a single beam of light, one standing still and the other on a speeding train. Common sense tells us that the person on the train should perceive the light traveling slower, since they are moving in the same direction. However, Einstein's theory states that both observers would measure the speed of light to be exactly the same, an incredible 299,792,458 meters per second. This seemingly paradoxical idea has been experimentally verified countless times, forcing us to reconsider our intuitive notions of space and time. The constancy of the speed of light has a mind-bending consequence. Time itself must be relative. To accommodate the constant speed of light, time must slow down for objects in motion relative to a stationary observer, a phenomenon known as time dilation. The faster an object moves, the slower time passes for it. This is not just a theoretical curiosity, it has real-world implications. Einstein's general theory of relativity, published in 1915, takes on the enigma of gravity. Newton described gravity as a force acting at a distance between objects with mass. Einstein, however, proposed a radically different view. He posited that gravity is not a force at all, but rather a curvature in the fabric of spacetime caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline, causing the fabric to sag. Now roll a marble across the trampoline. Its path will curve towards the bowling ball, not because of any force pulling it in, but because the trampoline itself is warped. Similarly, massive objects like stars and planets warp the fabric of spacetime around them, influencing the motion of objects in their vicinity. This warping of spacetime is what we experience as gravity. The Earth orbits the Sun not because of a mysterious force pulling it inward, but because it follows the curvature of spacetime created by the Sun's immense mass. General relativity thus provides an elegant and profound explanation for one of the universe's most fundamental forces. One of the most intriguing consequences of general relativity is the idea of time dilation caused by gravity. Just as time slows down for objects in motion, it also slows down in stronger gravitational fields. Imagine two identical clocks, one on the surface of the Earth and the other in orbit high above. The clock on Earth, experiencing stronger gravity, would tick slightly slower than the clock in orbit. This effect, though minuscule on Earth, becomes significant near extremely massive objects like black holes. A black hole's gravity is so intense that it warps spacetime to an extreme degree, creating a region where time appears to stand still for an outside observer. Time dilation due to gravity is not science fiction. It has been experimentally verified using atomic clocks. These concepts, while seemingly bizarre, are not just abstract theories. They have practical implications for technologies we use every day, like GPS satellites. These satellites rely on extremely precise timekeeping to determine location. However, because they are in orbit, they experience time dilation due to both their motion and the weaker gravity at their altitude. Engineers must account for these relativistic effects to ensure the accuracy of GPS systems.